Nobody is talking about the real reason Starship version 3 matters, and it has nothing to do with going to Mars. Here is what is actually happening. SpaceX just finished designing a rocket that can carry 100 metric tons to orbit, and then land itself to fly again. 100 metric tons. That is the weight of about 80 family sedans, delivered to space and brought back for reuse, potentially in the same week. No rocket in human history has ever done anything close to that combination of size and reusability. Not the Saturn V, not the Space Launch System. Nobody. And while most of the coverage you see focuses on Elon Musk talking about colonizing Mars, the engineers quietly building this thing in South Texas are solving a completely different problem first, one that is about to reshape every industry that depends on putting things into space. Let us start with the engine, because the engine is where the story actually begins. The Raptor 3 is not just an upgrade. It is a philosophical shift in how you build a rocket motor. SpaceX stripped out complexity. They removed parts. They made it lighter, somewhere around 1,525 kilograms per unit according to tracking by the aerospace community, and they pushed the thrust higher, into the range of 280 to 300 metric tons of force per engine. Now multiply that by 33 engines on the Super Heavy booster, and you get a combined liftoff thrust figure that some community analyses place near 10,000 metric tons of force. That number is so large it is almost meaningless until you compare it to what came before. The Saturn V, the rocket that sent humans to the moon, produced roughly 3,500 metric tons of force at liftoff. Starship version 3 is aiming for nearly 3 times that. The difference is that Saturn V was built to be thrown away after a single flight. Every single one of those engines, every fuel tank, every piece of precision hardware, gone after one use. SpaceX is building something designed to fly again and again and again, and the Raptor 3 is the component that makes the economics of that possible. Now here is the part that almost nobody in mainstream coverage is explaining clearly, and this is where it gets genuinely interesting. Version 3 is not just a bigger rocket. It is a rocket specifically designed to receive fuel in orbit. SpaceX engineers added dedicated docking ports and internal plumbing for cryogenic propellant transfer directly into the hull of the Starship upper stage. What that means in plain language is this. You launch a Starship loaded with cargo or passengers. It reaches orbit, but it does not have quite enough fuel to go to the moon or deep into space. So you launch a second Starship, this one acting as a tanker, carrying nothing but liquid methane and liquid oxygen. The two vehicles dock in orbit, transfer the propellant, and then the mission vehicle has a full tank and heads out to wherever it needs to go. It sounds simple. It is extraordinarily difficult in practice. Cryogenic propellants boil off constantly. They are stored at temperatures near negative 180 degrees Celsius. Getting two massive vehicles to dock gently, connect plumbing, and transfer hundreds of tons of fluid while both are floating in zero gravity is a problem that has never been solved at this scale. NASA and SpaceX have acknowledged that earlier estimates for a lunar mission called Artemis Human Landing System suggested something on the order of 10 or more tanker flights might be required to fully fuel a single Starship destined for the moon. Version 3 is the block of hardware designed to actually attempt proving this works, with dedicated demonstration missions reportedly planned for 2026. This is where you need to understand the stakes in terms that connect to real money and real industries. The global satellite launch market is measured in tens of billions of dollars per year. Right now, every satellite operator, every defense agency, every telecommunications company has to plan around launch vehicles that lift between 5 and 30 tons to orbit at significant cost per kilogram. Starship version 3, if it hits its reusable payload targets around 100 metric tons per flight, changes the fundamental economics of every single one of those contracts. You could launch an entire generation of Starlink satellites in one flight. You could deploy a military reconnaissance constellation in a fraction of the time it currently takes. You could send up a space station module the size of a small apartment building in a single mission. The physical constraint that has shaped the entire satellite and space infrastructure industry for 60 years, the tyranny of the kilogram and the cost to lift it, gets dramatically loosened. That is not a Mars story. That is an immediate, near-term industrial disruption story happening right now. Here is the question worth sitting with, though. Has anyone in your industry actually planned for this? Think about the companies that manufacture satellites. Their entire engineering culture is built around miniaturization, because every gram you save on a satellite saves enormous cost at launch. If launch costs drop by an order of magnitude and payload capacity multiplies by 3 or 4 times compared to current vehicles, those miniaturization constraints relax significantly. You can suddenly build larger, more powerful satellites with more capable hardware, because you are not paying a penalty for the extra mass. That changes the product. That changes the supply chain. That changes which companies survive the next decade, and which ones are still engineering for a world that no longer exists. The question for the comment section is this: do you think the aerospace and defense industry is actually prepared for what happens if SpaceX proves reliable orbital refueling by 2027? Or are the major contractors still quietly betting this takes another decade to matter? Now let us be honest about the risks, because the story is not complete without them. Every one of the capabilities described above is still unproven at operational scale. Ship-to-ship cryogenic refueling in zero gravity has never been done with vehicles this large. The Raptor 3 engine, despite significant testing at SpaceX's facility in McGregor, Texas, still needs to demonstrate the kind of flight reliability that allows rapid reuse without extensive inspection and refurbishment between missions. The early integrated Starship test flights resulted in spectacular and informative failures. SpaceX iterates through hardware faster than any other launch provider in history. But that iteration speed means the program has also produced real explosions over the Gulf of Mexico that required regulatory review and environmental assessment. The Federal Aviation Administration approvals, the launch licensing, the range constraints, all of those represent real friction that does not care about engineering ambition. Version 3 could demonstrate every technical milestone on the list and still face a 2-year regulatory backlog before it becomes a commercially operational launch system. The manufacturing picture is telling, though. Reports from the aerospace community and engine tracking observers throughout 2024 and 2025 indicate that Raptor 3 production is visibly ramping at McGregor. Hull fabrication at Starbase in Boca Chica shows increased activity. SpaceX made the deliberate design choice to simplify the engine, reducing part count and subassembly complexity, specifically because their longer-term goal requires building these vehicles at a cadence that would sound absurd compared to any previous rocket program. If the economics work, the goal is not to launch Starship once or twice a year. It is to launch it dozens of times, potentially more. That production ambition is either the most impressive industrial scaling in the history of rocketry or the most optimistic projection in aerospace since the 1960s, depending on how the next 18 months of test flights go. Compared to what has come before, the numbers are stark. The Saturn V could lift approximately 140 metric tons to low Earth orbit, but it cost the equivalent of hundreds of millions of modern dollars per launch and was never reused. The Space Launch System, NASA's current heavy lifter, reaches roughly 95 metric tons to low Earth orbit, costs over $4 billion per flight by some government accountability estimates, and is also expendable. Falcon Heavy from SpaceX, in its expendable configuration, reaches about 63 metric tons to low Earth orbit. Starship version 3 targets 100 metric tons or more in fully reusable configuration, meaning both the booster and the upper stage are caught or landed and prepared for the next flight. The marginal cost per launch, if reuse is actually achieved at scale, drops to a level that makes the Space Launch System's pricing look like chartering a private jet compared to a budget airline. So here is where this lands for you. If you work in any industry that touches satellite communications, defense technology, scientific research, or even early-stage space manufacturing, the next 2 years of Starship version 3 development are not a space enthusiast story. They are a business planning story. The vehicle being tested in the Gulf of Mexico right now is designed to do something no rocket has ever done: carry enormous payloads to orbit, refuel in space, and come home to fly again, at a cost structure that could make access to space feel less like a government program and more like a freight service. Whether that actually happens on schedule depends on engineering problems that are genuinely hard and regulatory processes that move at their own pace. What is certain is that the hardware exists, the plumbing is there, the engines are being built, and the first orbital refueling demonstrations are on the calendar. The conversation about what that changes for your world is worth having now, before the first successful transfer happens and everyone scrambles to catch up. If you want to keep tracking this story as the test flights happen, the refueling demos get attempted, and the real numbers start coming in, subscribe so you do not get caught flat-footed by the moment when the economics of space actually shift.